In this video, we discuss series solutions to differential equations. Now, so far in our course, we've studied reduction of order, which allowed us to find a second linearly independent solution of a second order equation given a first solution. We also studied methods for solving homogeneous linear ODEs with constant coefficients. Here we assumed that y was an exponential function, and we assumed it was y equals e to the mx, and then we found the right values of m to cause e to the mx to be a solution to that equation. We studied Cauchy-Euler differential equations. Those are differential equations that have a specific form. In that case, we can let y equal x to the m, and if we can find the values of m that satisfy a particular polynomial equation, we're able to find the solutions to the Cauchy-Euler differential equation. Now, all of these were used for homogeneous differential equations. Now, reduction of order can also be used for non-homogeneous differential equations, but we tended to focus on homogeneous equations. Now, for non-homogeneous equations, we studied two methods: the method of undetermined coefficients, which is a guessing method. If the corresponding homogeneous equation has constant coefficients and the right-hand side is an exponential function or a polynomial function or a sine or cosine function or some finite sum or product of those, we could make an educated guess about the form of y sub p, that particular solution. And usually starting with that guess and perhaps modifying that guess based on the form of the solution to the corresponding homogeneous problem, we could figure out what y sub p is by assuming it had the right form, and then it would have some undetermined coefficients in it, and we would find those undetermined coefficients. Now, if the corresponding homogeneous problem had variable coefficients, let's say if it was a Cauchy-Euler DE, we would have to use variation of parameters to find that particular solution. Or if the right-hand side was not an exponential, a sine or cosine, or a polynomial, or a finite sum of product of those, then we would have to use variation of parameters to find y sub p. Now, we've gone over a lot of specific cases, but there are many differential equations that don't fit into any of these categories. When all of these methods fail, this is what we're going to do. We're going to seek a solution in the form of a power series. And don't be scared, we're going to review power series right now, everything that you need to know from Calculus 2 in order to solve these problems and have a good sense of what it is you're doing and why you're doing it and what these actually represent. Now, if you remember from Calculus 2, power series are infinitely long. We can think of them like infinitely long polynomials. We're not actually going to find all of the coefficients of those infinitely long polynomials. We typically, when solving a differential equation, using a power series solution method, we typically just find the first few non-zero terms of various power series solutions. And then we use the partial sums of those power series, which are polynomials, to approximate the solution of the differential equation. Now, if a little bit of what I said there seemed cryptic because you don't really remember what power series are, not to worry, that's what this video is about. We're going to review some basics about power series. So here is our first definition. A power series is an expression of the following form. We have the sum, as n goes from 0 to infinity, of a sub n times t minus t naught raised to the n. Now, t naught is a given real number. We typically call that the center of our series. And the a sub n for n equals 0, 1, 2, and so on are constant coefficients. And we'll say they're also real coefficients. Now let me expand that just to make it a little bit more concrete. A sub n represents a constant, and that constant changes depending on what the value of n is. And T naught is a number, it's given to us. We call it the center of the series. And here's what this looks like in an expanded form. If I substitute in n equals 0 here, I get a sub 0 times t minus t naught raised to the 0. Anything to the 0 other than 0 is 1. So we'll have that. And then when n equals 1, we'll have a sub 1 times t minus t naught to the first. When n equals 2, you'll have a sub 2 times t minus t naught squared. Hope you see the pattern. This subscript keeps increasing, and the power of t minus t naught is the same as the subscript. So in n equals 3, a base of 3, and we'll be multiplying by t minus t naught cubed. And you just keep going forever. So it's like a polynomial, it's infinitely long, and typically this a sub 0, a sub 1, a sub 2, a sub 3, those are known. Like you're gonna have a function of n right here, and you'll be able to substitute that value for n, and then you'll have a number there. T naught is also known. So let me give you an example, or two or three. Here's an example. I have the sum as n goes from 0 to infinity of x to the n over n factorial. When n equals 0, we get x to the 0 over 0 factorial. And 0 factorial is defined to be 1. And of course, x to the 0 is 1. So when n equals 0, we just get a 1. Then when n equals 1, I'm just replacing n with 1 with x to the first over 1 factorial, which is just an x to the first. Then when n equals 2, we'll have an x squared over 2 factorial, x squared over 2, or I prefer to write it as 1/2 x squared. When n equals 3, you've got x cubed over 3 factorial. Hope you see the pattern. 3 factorial is 3 times 2 times 1, so that's a 6 in the denominator. I'll pull that out as a 1/6. So up 1/6 times x cubed, and you keep going on and on and on with this. The power of x and that number that you're taking the factorial of in the denominator, they match. And that's exactly what this says here. And you're just changing that value of n, starting with n equals 0 and incrementing up n equals 0, 1, 2, 3, and so on. Now, this is using the variable x rather than the variable t, but that's okay. We're not subtracting anything from that x. So that matches this form, but instead of t, I've got an x, and my x naught in this case would be 0, since we're not subtracting anything from the x. So this is a power series. Centered at x naught equals 0, because I'm not subtracting anything from these x's. And my coefficient, a sub n, is this number that we're multiplying that x to the n by. So it's that 1 over n factorial. So when I told you that that was a constant, that's our constant in this case. And in this case, a sub 0 is 1, a sub 1 is 1, a sub 2 is 1/2, a sub 3 is 1/6, a sub 4 will be 1 over 4 factorial, and so on. Let's look at another one. Here I have the sum as n goes from 0 to infinity of x minus 1 over 2, all raised to the nth power. You don't have to do this. But to make this look a little bit more like this up here, we might apply that nth power to the numerator and the denominator. A fraction to the n is just that numerator to the n over that denominator to the n. And then we could expand it just to have a sense of what's going on when n equals 0, when n equals 1, when n equals 2, n equals 3, and so on. So when n equals 0, I have x minus 1 to the 0 over 2 to the 0. Anything to the 0 is 1. Then when n equals 1, we'll have x minus 1 over 2. Or I'll factor out that over 2. That dividing by 2 is the same as multiplying by 1/2. When n equals 2, we'll have x minus 1 squared. I'll have 2 squared in the denominator, that's a 1/4. N equals 3, I'll have an x minus 1 cubed and a 2 cubed in the denominator. So that would give me a 1/8 out front. And we would continue in this way. Since we're subtracting 1 from all of these x's, that's our x naught. So this is a power series centered at x naught equals 1. And our coefficients a sub n are given by these coefficients. We've got a 1, a 1/2, a 1/4, a 1/8. Or over here, I'm thinking of a sub n as the factor that's multiplying that x minus x naught to the n. That factor is a 1 over 2 to the n. Okay, and let's do one more example where we'll just identify the center. Since we are adding 4 to this x value, x naught is -4. Here, the center is the value of t that would cause this expression in the parentheses to be 0, and t naught is a number. So the center of this series is t naught, because when t equals t naught, we'd get 0 there. The center of this one is 0. The center of this one is 1, because 1 minus 1 would give me the 0. Here, the center is x equals -4, because -4 plus 4 would give me 0, or you can think of this as x minus a -4. So we're subtracting -4, so that would make x naught equal to -4. And a sub n is the formula for the coefficient of that x minus x naught to the n. In this case, our a sub n is n factorial. So let's substitute n equals 0, n equals 1, n equals 2, n equals 3, just to get a sense of the pattern. So I have 0 factorial, which is defined to be 1, times x plus 4 to the 0, which is 1. And then when n equals 1 here, we have 1 factorial times x plus 4 to the first. When n equals 2, we'll have 2 factorial, which is 2, times x plus 4 squared. Then the next one is 3 factorial. 3 factorial is 3 times 2 times 1, which is 6. And then we've got an x plus 4 cubed. And you keep going. Oops, I don't need a plus sign there. So that's the n equals 0 term, n equals 1, 2, 3, and so on. So as you can see, these power series are just like polynomials, they're just infinitely long. The coefficients are functions of which term you're on. I've got a coefficients of 1, 1, 1/2, 1/6. Coefficients here of 1, 1/2, 1/4, 1/8. Here, 1, 1, 2, 6, and so on. And the center, again, is defined by the x value that will cause that x plus or minus a constant raised to the n to equal 0. Or you can think of it as the x value that you're subtracting, or the number that you're subtracting from the x. So I'm subtracting a 1 from the x, so the center is 1, or I can say that would equal 0 when x equals 1, so the center is 1. This would equal 0 when x is equal to -4, or you can say you're subtracting a -4 from the x. So that's centered at 0, 1, and -4. All righty. always like to make my notes kind of pretty. It's always good to have boundaries too. Get some nice, pretty boundaries there. Okay, so we're adding up these polynomial expressions, powers of x. We've got infinitely many of them. You might say to yourself, what does it mean to add infinitely many numbers? Well, that question is typically covered in Calculus 2, but I will define convergence for us now. We'll say that the power series that we just referred to, that sum as n goes from 0 to infinity of a sub n times t minus t naught to the n is said to be convergent at a particular value of t if the following is true. If the limit as n goes to infinity of a sub 0 plus a sub 1 times t minus t naught to the first plus a sub 2 times t minus t naught squared, and so on. This is the sum of the first n terms. We're going to stop at a sub n times t minus t naught to the n. If I take the limit of that as n goes to infinity, so as if I'm adding infinitely many terms here. If that limit is a function of t, if that limit exists, then we call that function of t the sum of the series. Now, this is typically denoted by s sub n. We'll call it s sub n of t. This is called the nth partial sum of the series. So it's like a truncated power series. It's polynomials of different lengths. And the partial sum, sorry, let me write that out. We'll scratch that out, partial sum. And the partial sum of the series. If the limit of the nth partial sum is some function of t, then we say that this function of t is called the sum of the series. Now, I recognize that this is pretty abstract for most of my students. So let's make it a little bit more concrete. Let's look at a particular power series. So we have the sum as n goes from 0 to infinity of x minus 1 to the nth over 2 to the n. Now, we expanded this earlier. We said when n is equal to 0, we get 1. When n is equal to 1, we get 1/2 times x minus 1 to the first. When n is equal to 2, we get 1/4 times x minus 1 squared. N equals 3, we get 1/8 times x minus 1 cubed, and we keep going forever. Got infinitely many terms, we're adding them together. And the question is, does this converge to something? The way you want to think of this is you want to think of it as a function of x, or in this notation up here, we're using t as the independent variable. So we're thinking of it as a function of t. In this example, we've got a function of x here. And the question is, if I plug in a particular x value, will this sum converge to something? So let's just substitute. Let's see if this, let's substitute a particular x value. Let's substitute x equals 2. So we could think of this as a function of x. I'll just call it f of x. I'll say f of 2 equals what? So now I've got the sum as n goes from 0 to infinity of 2 minus 1 to the nth over 2 to the nth. Of course, that's just going to give us a 1 to the n in the numerator. 1 to any power is just going to give me a 1. So we have that. So we're going to have 1 plus, when n equals 0, we get 1. When n equals 1, we get 1/2. Then we'll have 1/4, then 1/8, then 1/16, and we'll keep going. Now what I just did was I substituted into this formula that I got from simplifying this, but you could have just as easily substituted x equals 2 up here, but every time you plug in x equals 2, you're going to have 2 minus 1. So that's going to be a 1, that's going to be a 1 squared, that's going to be a 1 cubed. So we end up with the 1/2 or 1 plus 1/2 plus 1/4 plus 1/8 and so on. The question is, at x equals 2, does this converge to a number? And it turns out that it does. From calculus 2, we know that this is what's called a geometric series. In order to get from term to term, we multiply by the same constant. To get from 1 to 1/2, I multiply by 1/2. And if I can do that again to get to the next term, and I can do that again to get to the next term, and that's true for all the terms, then it's called a geometric series. So 1 times 1/2 gives me 1/2. This times 1/2 gives me 1/4. This times 1/2 gives me 1/8. 1/8 times 1/2 gives me 1/16. And we keep going. So this is geometric. And this number that we multiply by over and over again, it's called the common ratio of that geometric series. The common ratio is 1/2. Now, back in calculus 2, you learned this. Hopefully your teacher gave you a proof of this in class, or you went through the derivation for the sum of a geometric series. We said this, a geometric series will converge to the first term over 1 minus the common ratio. Now, typically the notation used is a over 1 minus r. The notation isn't that important. The important part is that you get from term to term by multiplying by the same constant every time. The first term goes in this numerator. 1 minus the common ratio is what goes in the denominator, and the common ratio is that number that you're multiplying by. So that's our r. And so we have 1 over 1/2, which is 2. So it turns out you're able to add this 1 with all of these infinitely many positive fractions, and they're getting so small, so fast that when you add them all together, the sum of that is 2. So that means x equals 2 works. This converges for x equals 2. We might be interested in finding out all of the x values where this converges. We call that finding the interval of convergence. It's like finding the domain, but it's just finding all the x values that you can plug in where you actually get a sum out of that infinite series, where you're able to, where you're able to add all of those infinitely many numbers together, and there is a single number that comes out from that. Now, before I get too far ahead of myself, I just want to talk more about the sum of this series, the partial sums of this series. For this particular example, S sub 0 is just a sub 0. It's the term that we get when we plug in n equals 0. So it's just 1. S sub 1 is a sub 0 plus a sub 1. It's the sum of those first two terms. S sub 2 is the sum of the first three terms, a sub 0, a sub 1, and a sub 2. So we're going to take that, and that now. And you would keep going. S sub n is the sum of a sub 0, a sub 1, a sub 2, all the way through a sub n. And the question is, does that series converge to a function of x in our case, or t in this case up here? Do we get a single function of t? Of course, it's easier to think about when we're imagining substituting in a particular x value. So these are the partial sums for my power series, but the corresponding partial sums when x is equal to 2 are these. We've got s sub 0, which is 1, s sub 1, which is 1 plus 1/2, which is 3/2. S sub 2 is 1 plus 1/2 plus 1/4. So that's going to be 7/4. S sub 3 is 1 plus 1/2 plus 1/4 plus 1/8. If you actually do that arithmetic, you're going to get 15/8. And so on. It turns out that the pattern is this. We always end up with 2 times, well, actually, no, it's not 2 times that. In the denominator, we end up with 2 to that power. So I've got 2 to the first there, 2 squared there, 2 to the third there. So when this is n, we'll have a 2 to the n here. And in the numerator, what you end up with is 2 to the n minus 1 plus, and then you're going to add an extra 1 to that. Maybe that's a little hard to see. So this is going to give me, when n is equal to 3, I'd have 7/8 plus 8/8, which gives me that 15/8. When n is equal to 2, I'll have 3/4 plus 4/4, which gives me the 7/4, and so on. So that's the nth partial sum for that series when x is equal to 2. Now the question is, like, I don't want to have to just do this through trial and error. What other x values can I put in there? And what other x values will give me an infinite series that actually converges to some number? And sometimes we may want to know, is it possible to find that number, not just for a particular x value, but for a general x value? Can we find the s of t, or in this case, can we find the s of x or f of x? Can we find that function so that this series converges to that function for all x in some interval? And then there's the other question, like what interval? What interval will work? What x values can we put in so that the sum of the series exists, so that this limit exists and it's finite? That set of x values that you can plug in here so that this series converges is called the interval of convergence of that power series. It's kind of like the domain, but we're dealing with power series. So we're thinking of the power series as a function of x, and we're asking ourselves, which x values can we put in so that the power series converges? If we're thinking of our power series as functions of x, the set of x values. If we're thinking of our power series as functions of t, that would be t values, or just values of the independent variable. For which the power series converges. Now I defined, I defined convergence in this way. I said that the power series converges at a value t if the limit then goes to infinity of this nth partial sum converges to a function of t for that particular value of t. I didn't mention this other definition. Here's another definition before we talk about something else. Absolute convergence. We say that a power series, and let's use that first form that we started with, the sum as n goes from 0 to infinity of a sub n times the quantity t minus t naught to the n. We say that that power series is absolutely convergent if the series of absolute values of this converges. Now, the series of absolute values is going to look like this. Well, the sum as n goes from 0 to infinity of the absolute value of a sub n, and this will be the absolute value of t minus t naught raised to the n. If this converges, then we call the original series absolutely convergent. Okay. And now I want to define another term for you. It's called the radius of convergence. Of a power series. Now, the radius of convergence is a non-negative number we're going to use rho such that the series is absolutely convergent when the absolute value of t minus t naught is less than rho, and divergent when the absolute value of t minus t naught is strictly greater than rho. So let's graph this just to make it clear. Here's t naught. I'm talking about the absolute value of t minus t naught, and I'm saying that that's less than rho. That's equivalent to saying that this t minus t naught is in between negative rho and rho. So if I add t naught to all three parts of this inequality, I get this. Now, that might look like Greek. It's because it is, in part it is. But I want you to notice the form of this limit on the left and the limit on the right. Both of them start with t naught, and then we're subtracting rho and we're adding rho. So I've got t naught here. I'll add rho and I'll subtract rho. The radius of convergence is that non-negative number rho, so that the series is convergent on this interval. So the series converges here. But then it diverges outside of that interval. That absolute value will be strictly greater than rho over here. When t is greater than t naught plus rho, or when t is less than t naught minus rho. In that case, rho is called the radius of convergence. Now, notice I didn't say anything about this endpoint or that endpoint. That's questionable. If we know what our radius of convergence is, we know that our series converges on this interval and diverges outside the interval, but what happens at the endpoints is questionable. It may converge at the endpoints, or it may not converge at the endpoints. Okay. And all of this is related to this idea of an interval of convergence, a set of X values for which our power series is guaranteed to converge. And the radius of convergence, the interval of convergence is the entire interval where it converges, which might be this, or it might be this, including the endpoints, or one of the endpoints, or neither of the endpoints. And the radius is half the length of that interval. It's the distance from the center to one of those endpoints. Now, there are three possibilities when it comes to intervals and radii of convergence of power series. Now, let's assume that we're starting with this power series, and I'm just going to write it as f of t. F of t is equal to the sum as n goes from 0 to infinity of a sub n times the quantity t minus t naught to the n. Given that t naught is the center, here are your possibilities. Your interval of convergence is typically denoted by I, and it's possible that your series just converges at the center, t naught. Then we would write it like this. It's a pretty boring interval, it's just a single point. In that case, the radius of convergence, in calculus text, it's typically denoted by r. In one of the differential equations texts that I'm looking at, it's the Constanda differential equations text. We're using this notation rho. Here we would say that rho or r is equal to 0. Now I'm going to switch from using that r all the time, which is what's used in calculus classes typically, to rho from now on. Rho is the radius of convergence. So I've got, we could have a power series that converges at a single point, just converges at the center. So our power series converges at the center only. In that case, rho is equal to 0 or r is equal to 0. The other possibility is that r is a finite number. R is greater than 0 and r is finite. Oh, I keep shifting back to r because I'm used to it from teaching calculus. Just another notation for exactly the same thing. Here we go. In that case, our interval of convergence will look something like this. We go from t naught minus rho to t naught plus rho. Usually we would have an x naught minus r, x naught plus r if we're using that notation from calculus. And our series converges in there, and it may or may not converge at the endpoints. So you actually have 4 possibilities here. The series might converge on an interval that looks like this, or the interval might include both endpoints. The interval might exclude the left endpoint and include the right endpoint, or vice versa. And then the third possibility is that, and I kind of hate this notation, r is infinite. That just means that our interval of convergence is the entire real line. So there's t naught, and the interval from negative infinity to infinity is our interval of convergence, or you can just write it as the r with the double bars. Or using this new notation, rho is equal to infinity. So we've got our interval of convergence here, radius of convergence here. I want to give you a few examples. I'm not going to go through all of these. These examples are probably better left in a Calculus 2 course. But just to remind you, here's a series that only converges at its center. because I'm multiplying by that factorial. That factorial is growing. It's growing fast. We add all of those numbers together. We're never going to get a sequence of partial sums that converges to a function of x. It's always going to go to infinity, unless x is equal to the center. If x is equal to -4, then we're going to have, well, actually, yeah, this will only converge at the center at x equals -4. So this converges on the interval I, which is the degenerate interval, -4, and has a radius of convergence, which I'm going to use it this time, rho, equals 0. And let's see, if I want one where r is finite, how about that one that we were looking at before, x minus 1 to the n over 2 to the n for n between 0 and infinity. This is a geometric power series, and it converges on this interval. It's going to be the set of all x values as such that x minus 1 over 2 is less than 1. Absolute value of x minus 1 over 2 is less than 1. I'm actually taking the common ratio here. This is called a geometric power series because as you go from term to term, you're always multiplying by that x minus 1 over 2. This will converge when that common ratio is, or the absolute value of that common ratio is less than 1. So here we'd have x minus 1, or the absolute value of x minus 1 would be less than 2. That means that x minus 1 is between 2 and 2. Or if we add 1 to all 3 parts, we get the interval from -1 to 3 is our interval of convergence. And our radius of convergence is equal to 2. Now I know that that was a quick calculation and I made a reference to something in calculus 2 that you've probably forgotten, and that's okay. I just wanted to give you an example of one that only converges for some x values. As long as x is between -1 and 3, I can plug that value in here and I'm going to get a number out. But if I choose, say, x equals 4, x equals 0, or not x equals 0, or x equals -2, numbers outside of that interval, it's not going to work. And then this series turns out to be the Maclaurin series for e to the x. This one converges for all real numbers. So you can write that as the r with the double bars or the interval from -infinity to infinity. In that case, we would say that our rho or our r is infinite because you've got the entire real line. And that's what happens when it comes to power series. You either converge, the power series either, converges at the center or an interval around the center or the entire real line. It never converges for an interval and then skips some t values and then converges on another interval and skips some values. That's not how it works. It always has either this pattern at the single point, at the larger interval, or the whole line. And those are some examples where you would have the various cases. On this one, only x equals -4 will work. On this, as long as x is in this range, we're good to go. If x is outside of that range, that sum diverges. And here, this one turns out to converge to e to the x all the time, no matter what x is. Now, just to make that a little bit more concrete, I know we've already looked at the example where x was equal to 2, and we substituted that in here. That turns out to be part of that interval of convergence for this one. Let's see what happens when x is equal to 3. Actually, let's not use x equals 3 because that was the boundary. Let's use x equals 4. If this is a function of x and I try to substitute in x equals 4, this is what I would get. And this is questionable because maybe it's not actually a function because that sum diverges. If we simplify this, we've got a 3 to the n in the numerator and a 2 to the n in the denominator. And remember, if you've got a to the n over b to the n, you can write that as a single fraction to the n. That's 3 over 2 to the n. So when n equals 0, we get 3 over 2 to the 0, which is 1. When n equals 1, we get 3 over 2. When n equals 2, we get 9 over 4. When n equals 3, we get 27 over 8. The next one would be 81 over 16, and so on. You just keep going. Now notice we're multiplying by 1.5 every time. So the terms themselves are getting larger and larger and larger, and they're going to infinity. So if I'm adding numbers that are going to infinity themselves, like if I was just looking at the numbers, the 3 over 2 to the n, that would be going to infinity. But I'm not just looking at the numbers, I'm looking at the sum of those numbers. So the partial sums here would be s sub 0 equals 1, s sub 1 equals 1 plus 3 halves, which is 5 halves. S sub 2 is 1 plus 3 halves plus 9 over 4. So that's 5 halves times 2 over 2 plus 9 over 4, 19 over 4, and so on. That's 2.5. Then we have 4.75, and you just keep going. So here I'm taking my 4.75, and then I'm adding this 27 over 8. You see that that's just going to get larger and larger. It says n goes to infinity, s sub n is definitely going to go to infinity. Now, I haven't come up with a formula for that. If I was in calculus 2, I'd try to come up with a formula for that and show that the limit as n goes to infinity of s sub n equals infinity. But for right now, since we are in differential equations and just reviewing this, I want to just make sure we understand the concept. Since this limit of the nth partial sum is infinity, that means this f of 4 is undefined. And the series diverges. At x equals 4, our power series does. Now, I mentioned the 3 possibilities. Either converge at a point, you converge on an interval, or converge on the entire real line. All of that is true. But if you want to know where the power series converges, you've got 2 possibilities, 2 options. So if I want to determine the interval and radius of convergence, it really depends on the form of that power series. But if the power series is geometric, so that to get from term to term, we're always multiplying by that same thing, that common ratio r of x. We'll use the geometric series test. To determine the radius of convergence. So you'd say, what am I multiplying by to get from term to term? We'll let r of x equal the common ratio. And in that case, once you've identified the common ratio, the geometric power series will converge when the absolute value of that common ratio is less than 1. And of course, there's more detail about this when you take calculus 2. And you would just solve that inequality for x. Once you have that interval of x values, you could just take the length of the interval, divide by 2. That's going to give you the radius of convergence. The interval itself is, of course, the interval of convergence, the open interval of convergence. And you have to test the endpoints. Now, if the power series is not geometric, you don't get to use this shortcut. In that case, you would use the ratio test. And the ratio test will allow you to find both the interval and the radius of convergence. Now, both the geometric series test and the ratio test allow you to find the interval where that power series is absolutely convergence. And that's what we want. Now we have a couple of more facts and definitions that we want to review in preparation for finding infinite series solutions to differential equations and thinking about where those series converge and diverge. Here are a few notes. If you have power series with the same center and radius of convergence, those power series can be added, subtracted, multiplied, and differentiated term by term, and the result will always be a series with the same radius of convergence. So let's list those. They can be added, subtracted, multiplied, and differentiated. Term by term. So it's kind of like when you're adding, subtracting, or multiplying polynomials, or differentiating a polynomial. You just differentiate one term at a time. That's possible when you're dealing with power series, and the result will always be a series with the same radius of convergence. Now, the convergence may differ at the endpoints of that interval of convergence, but it's not our primary concern here. We just want to know, when can we add these, subtract them, multiply them, and differentiate them? When they have the same center and radius of convergence, you can. Another thing that will come in handy, is this another fact that will come in handy is the fact that power series are equal. Missed a word there, are equal if they have the same coefficients. Now we need a few other terms before we talk about the convergence and divergence of series solutions to differential equations. We need to know what an analytic function is. In order to do that, we need to review what it means to be a Taylor series. So here's a definition. Let's let f be infinitely differentiable. Just means we can take the derivative as many times as we want. At t naught. If f is infinitely differentiable at t naught, then f has a Taylor series expansion about t naught. And we might write it this way: f of t is associated with this series. It's the nth derivative of f evaluated at t naught divided by n factorial times t minus t naught to the nth. Just as a reminder, this is prime notation for the nth derivative of f evaluated at t equals t naught. Of course, these are just numbers that depend on the function f times t minus a number to some power. We're adding all of those together. So this is a power series. It's a special power series where these are the coefficients. I'll just write every Taylor series is a power series. And if I want to expand this, this is what I would get if I substitute in n equals 0. Well, the 0th derivative of f at t naught, that's just the function at t naught, times t minus t naught to the 0, which is 1, over 0 factorial, which is also 1. So we just got f of t naught. Then when n is equal to 1, we'll have f prime at t naught times t minus t naught to the first. When n is equal to 2, we're going to have a 2 factorial in the denominator. So that's going to give us a 1/2 out front times the second derivative at t naught times t minus t naught squared, plus more terms, infinitely many of them. Now, these are the only unknowns in this. If you've taken calculus 2, you probably remember trying to find a Taylor series for a function centered at a particular point. Typically, what you would do is you'd try to find a pattern for that nth derivative of f evaluated at a particular value t naught or x naught or c, depending on the book, you use different notation. But you're just trying to find that pattern. And this is just a constant plus a constant times t minus t naught to the first, 1/2 times a constant times t minus t naught squared, and so on. And you would typically try to find the value of that constant. Now here is another definition. We say that f is analytic at t naught if the Taylor series of f centered at t naught converges to f of t in some open interval containing t naught. So basically, we're saying that the radius of convergence is not 0. We've got some interval of convergence that at least looks like this, perhaps looks like that. If that's the case, we say that f is analytic at t naught. And then that function is actually equal to its power series over that interval. So rather than using this tilde, which says that this function is associated with this series, this function is used to generate or derive this series, we're saying that if f is analytic at t naught, those are actually equal to each other on some interval. Now we talk a little bit about this idea that a Taylor series converges to its generating function. in Calculus 2. We're not going to emphasize that so much here, but we're just going to say if it does, if this series converges to this function, rather than using the tilde, we'll use an equal sign, and then we will say that that function is analytic at that t naught. So I always use my equal sign for the Maclaurin series for e to the x, because the Maclaurin series for e to the x converges to e to the x for every x value in the entire real line, or on the entire real line. Okay, some more notes. If f and g are analytic at t naught, then f plus g is analytic at t naught, f times g is analytic at t naught, and f over g is analytic at t naught as long as the denominator is non-zero. Now g of t naught can be 0 for these first two. It just can't be 0 for that one because of course you're dividing by it, and we don't ever want to divide by 0. Now a couple of other notes. One is that polynomials are just terminating power series. So if I have a polynomial, let's just say x squared minus 3x plus 1, I can think of that as 1 plus negative 3 times x plus 1 times x squared plus 0 times x cubed plus 0 times x to the fourth, and so on. So this is a power series. I could say that's c naught plus c1x plus c2x squared plus c3x cubed, and so on. So in this case, c naught would be equal to 1 because two series are equal if their coefficients are equal. The coefficient of x here would equal the coefficient of x there. So c1 would be negative 3, c2 would be 1, c3, c4, and so on. After that, those are all 0 because we just have this polynomial over here. So we might say c sub n is equal to 0 for n equals 3, 4, 5, and so on. So every polynomial is a power series. We can think of it as a terminating power series. Now this is expanded about x equals 0 because I'm not subtracting anything from the x's over here, but I could expand this power or this polynomial about a different point. I'm not going to do that because it's sort of getting off on a tangent, honestly. But we could expand any polynomial about any point and come up with the appropriate coefficients over here. But if you have a polynomial, it will always be a terminating power series, and you can change that center x equals x naught or t equals t naught as you want to. Now, since it's a terminating power series, that means that the interval of convergence for this, or the interval of convergence for this, will definitely be all real numbers. And that's important to us because most of the coefficients that we'll be looking at in our differential equations will be polynomials. So we've got polynomials, they're terminating power series, which makes them analytic functions. And we know that they have an interval of convergence of all real numbers and a radius of convergence. Of rho equals infinity. Now, rational functions, remember those are polynomials divided by polynomials. Are analytic as well. Remember what it means to be analytic. We're saying that this function can be represented in a power series by a power series that would typically be given by its Taylor series. This is true as long as T naught is not a zero of the denominator. We don't want to divide by zero. Now, if the denominator is 0 when t equals 3, we're going to have a different series representation to the left of 3 than we would to the right of 3. We'd end up with different power series for those rational functions. But we could find a power series that represents that function at any t naught that does not cause the denominator to be 0. And the rational functions matter to us because the coefficients of our differential equation tend to be polynomials, and when we divide them, we get rational functions. Okay. Now, let's talk about differential equations just a little bit, and then in another video, we can talk about solving differential equations. So let's say we've got this differential equation, P of t times y double prime plus Q of t times y prime plus R of t times y equals 0. So it's a second order linear differential equation with variable coefficients. And we're assuming that P, Q, and R are given analytic functions. We say they're analytic, that just means that they can be expressed as Taylor series or power series. There are series that converge to these functions. Now, if P of T naught is equal to 0, we say that T naught is a singular point of the differential equation. Now, if P, Q, and R are well defined at T naught, and P of T naught is not equal to 0, then we say that T naught is an ordinary point of the differential equation. So let's make these definitions a little bit more concrete. By looking at some differential equations. So let's say this is our differential equation. Let's say you've got t plus 2 times y double prime minus t squared times y prime plus 3t minus 1 times y equals 0. If I want to find the singular points of this differential equation, I take my leading coefficient function, I call that P of t, and I set that equal to 0. So we set that equal to 0 and solve for t. That means t equals -2. Actually, I don't think it's equivalent. If I'm setting this equal to 0 and solving, then t is equal to -2. And that would be a singular point. Of the differential equation. Now, if t equals -2 is the only singular point of this differential equation, then any other real value t is an ordinary point. Okay. That's our P of t, and that was Q of t, and that's R of t. Those are the labels we're going to use in this course. Let's say you've got t plus 1 times t minus 3. Here, my P of t is this product. Sometimes it's not factored. Sometimes you've got to factor it yourself. P of t is equal to 0 when t is equal to -1, or when t is equal to +3. So that means that t equals -1 and t equals +3 are singular points of this differential equation. And all other values of t in the real number system are ordinary points. Of the differential equation. Okay, so we've got that terminology under our belt. Next time, we're going to talk more about power series solutions of differential equations that look like this, and where those series solutions are guaranteed to converge based on the singular points and ordinary points of this differential equation, and these coefficient functions, P of t, Q of t, and R of t. So that is for next time. I hope to see you then. I guess you'll be seeing or hearing me then. I won't be seeing you.